As I've mentioned in the past, this class is a large majority of it is mathematically formalizing common sense. The first chapter is going to be speaking mathematically, where we get the mathematical formal definitions of some structures and items that we'll be using later on in the semester. First off, we're going to do is get this to work right. Try this again. Okay. All right. There it is. First off, we're going to be talking about variables. A variable is sometimes thought of as a mathematical John Doe because you can use it as a placeholder when you're talking about something else. But either you don't know what value the item has, or if you want whatever you say to be equally true for all elements of a given set. So you don't want to be restricted to considering any particular value for that item. For example, okay, let's see here. Is there a number with the following property? Doubling it and adding 3 gives the same result as squaring it. You would introduce a variable to replace the potentially ambiguous word it. Is there a number x with the property such that 2x plus 3 equals x squared? The advantage of using a variable is that it allows you to give a temporary name to what you are seeking so that you can perform concrete computations, mathematical manipulations, that sort of thing, with it to help discover its possible values. This slide talks about the use of a variable as a placeholder. You can think of it as a box. The box can be any value or a particular value that you're not aware of yet. So you solve for the box. In this sense, a variable in a computer program is similar to a mathematical variable because it creates a location in computer memory, either actual or virtual, into which values can be placed. The second use of variables, consider the statement, no matter what number might be chosen, if it is greater than 2, then its square is greater than 4. In this case, introducing a variable gives a temporary name to the number. You might choose, it makes it so you can maintain the generality of the statement, and replacing all instance of the word it by the name of the variable ensures that possible ambiguity is avoided. So no matter what number n might be chosen, if n is greater than 2, then n squared is greater than 4. So use variables to rewrite the following sentences more formally. Are there any numbers with the property that the sum of their squares equals the square of their sum? So how would that be? So are there numbers a and b with the property that a squared plus b squared equals the sum of a plus b quantity squared, that the two values are equal? Given any real number, its square is non-negative. So any real number r, its square, r squared, is going to be greater than or equal to 0. So it gives the solutions here. A squared plus b squared equals a plus b quantity squared. And there's different ways of writing it. writing the same statement. That's one of the reasons why you mathematically formalize things, because English can be a little bit ambiguous and a little all over the place. There's lots of different ways of expressing the same thing in English. Given any real number r squared is non-negative. So I think I said the second one there on the previous slide. Some important kinds of mathematical statements. Three of the most important kinds of sentences in mathematics are universal statements, conditional statements, and existential statements. A universal statement is it says that a certain property is true for all elements in a set, like all positive numbers are greater than 0. A conditional statement says that if one thing is true, then some other thing also has to be true. Like if 36 is divisible by 18, then 36 is divisible by 6. They use a bigger number, but same principle applies. Given a property that may or may not be true, an existential statement says that there is at least one thing for which the property is true. There is a prime number that is even, which is true, the number 2. Universal conditional statements. Universal statements contain some variation of the words forever, every, and conditional statements contain versions of the words if then. A universal conditional statement is a statement that is both universal and conditional. Here is an example. For every animal A, if A is a dog, then A is a mammal. One of the most important facts about universal conditional statements is that they can be written in ways that can make them appear to be purely universal or purely conditional. So if A is a dog, then A is a mammal. That is conditional. Or it can be universal with, for every dog A is a mammal. So, or all dogs are mammals. Fill in the blanks to rewrite the following statement. For every real number x, if x is non-zero, then x squared is positive. A little audience participation here. If a real number is non-zero, then its square is? Audience participation. Then its square is positive. For every non-zero real number, x, positive. X squared is greater than 0. If x does not equal 0, then x squared is greater than 0. If the square of any non-zero real number is, or the square of any non-zero real number is positive, yeah. All non-zero real numbers have positive squares, yeah. All right, let's see here. Is positive, x squared is positive, is a non-zero real number, and x squared is positive, positive squares that are positive. Let's see here, universal existential statements. So a universal existential statement is a statement that is universal because its first part says that a certain property is true for all objects of a given type. And it is existential because its second part asserts the existence of something. For example, every real number has an additive inverse. In this statement, this property has an additive inverse applies universally to all real numbers. So it's a universal statement. Has an additive inverse asserts that the existence of something, an additive inverse for each real number. Therefore, it is existential. So the nature of an additive inverse depends on the real number. Different real numbers have different additive inverses. Knowing that an additive inverse is a real number, you can rewrite the statement in several ways, some less formal and some more formal. All real numbers have additive inverses. For every real number r, there's an additive inverse for r. And for every real number r, there's a real number s such that s is an additive inverse for r. Some examples there. One of the most important reasons for using variables in mathematics is that it gives you the ability to refer to quantities unambiguously throughout a lengthy mathematical argument, while not restricting you to consider only specific values for them. So you can take the details of what the variable stands for and just use the variable consistently throughout a mathematical argument and substitute back in the value of the variable at the end, as we'll see later on in some logic situations. Let's see here. Fill in the blanks to rewrite the following statement. Every pot has a lid. All pots have lids. For every pot P, there is a lid L. For every pot P, there's a lid L such that L is a lid for P. Yeah. So, let's see here. Existential universal statements, where they are reversed. An existential universal statement is a statement that is existential because its first part asserts that a certain object exists and is universal because its second part says that the object satisfies a certain property for all things of a certain kind. Like, there is a positive number that is less than or equal to every positive integer. So there is a positive integer, existential, that is less than or equal to every positive integer, universal. So this statement is true because the number 1 is a positive integer and it satisfies the property of being less than or equal to every positive integer. You can write it in several ways, some less formal, some more formal. And we're trying to keep things pretty formal in this class. So you would probably say something along the lines of the last one. There's a positive integer m with a property that for every positive integer n, m is less than or equal to n. Fill in the blanks. There's a person in my class who is at least as old as every person in my class. So some blank is at least as old as blank. Some person is at least as old as every other person, or as every person. There's a person P in my class such that P is older than every person in my class. There's a person P in my class with a property that for every person Q in my class, P is older than Q. as old as Q. Sorry, at least as old as Q. Yeah. Person in my class, every person in my class. Yeah. Some of the most important mathematical concepts, such as the definition of limit of a sequence, can only be defined using phrases that are universal, existential, and conditional. And they require the use of all three phrases: for, every, there is, and if then. So for the definition of what is it? Let's see here, the definition of a limit of a sequence. Okay. The limit the limit of a sub n as n approaches infinity is L, means that for every positive integer epsilon, that's universal, there is an integer n, existential, such that for every integer little n, again universal, if little n is greater than big N, then that equation is true. And that would be conditional. So it uses all of the above types of statements combined into one. There are lots of different combinations you can do with the three different types of mathematical statements. Be a lengthy day if we went through them all. So here. Next, we'll get into sets. The use of the word set as a formal mathematical term was introduced in 1879, not even 150 years ago. For most mathematical purposes, we can think of a set intuitively, as Cantor did, simply as a collection of elements. So you can define a set using set roster notation. So if set S is a set, if S is a set, notation X with the stylized E here, that means that X is an element of S. With a line through it, X is not an element of S. Set roster notation is typically done by writing all the elements between curly braces, like this right here. With a large set, you could use ellipsis to show a range, or you can have an infinite set with an ellipsis before or after the numbers in the set roster notation. If I'm not mistaken, this is similar to how you would define an array in C++, right? Done that way? Yeah. I'm not real strong on C++. I have to be reminded of that one every so often. The axiom of extension says that a set is completely determined by what its elements are, not the order in which they might be listed or the fact that some elements might be listed more than once. In this respect, it is different from an array. An array is ordered and duplication does matter. With sets, duplication doesn't matter, order doesn't matter. So A, B, and C here, the sets, you have 1, 2, and 3, just different order, and sometimes repeated. So are they equal sets? Yeah. They are equal sets. They are considered equal sets. Is the set of 0 equal to 0? No. That is a number. That is a set. Two different data types. So they are not the same. How many how many elements are in the set given here? Ooh. 1 is the number 1, and the second element is the set that contains the number 1. Because these are two different data types, integer, set, they are two different elements. Let's see here. For each non-negative integer n, let u of n sub n equal n comma minus n. So what would u1 be? U sub 1. 1 comma negative 1. Because you're defining it as being u of n as being the set of n comma the additive inverse basically of n. So 2, u sub 2 would be positive 2 and negative 2. And u of 0? Or just plain 0, because duplication doesn't matter. So, yeah, we got there's the same 3 elements, different orders, and repetition. And again, the set containing the number 0 and the 0 is different. But yeah, 1 comma minus 1, 2 comma minus 2, and 0 comma minus 0, which is 0 comma 0, which is equal to the set with just 0 as an element. Now, certain sets of numbers are so frequently referred to that they are given special symbolic names. These are summarized in the following table. R is the set of all real numbers. Z is the set of all integers. Where they get the Z for that, I don't know. But Q is for the quotient of integers or rational numbers. There's also another one. I am going to add to this. Hello? Come on. Come on. Sometimes these these smart boards aren't very smart. There we go. And they're gonna let me draw here? Okay. Okay, the fourth set is the natural numbers. Believe it or not, 0 is not a natural number. For many, many millennia, the number 0 was not recognized as being an actual number. It wasn't a natural development of human thinking. I forget exactly who first introduced the concept of the number 0, but Arabic number system that we use today was how it was introduced to Europe. You've seen Roman numerals before? Okay, there is no 0 in Roman numerals. In ancient Rome, Yeah. Come on. In ancient Rome, they used if they said like 2 minus 2, the answer was nihil, nothing. It wasn't a number. Nihil is where we get the word annihilate, that sort of thing. But nihil was the word for 0. Just it meant nothing. There's nothing there. There's no counting anything. But anyway, a little side tangent about numerical history. My high school Latin teacher would be proud of me for remembering that term. Okay, let's see here. The addition of a superscript or a subscript, a superscript of plus or minus, or the letters non-negative indicate that only the positive or the negative or non-negative elements of the set are to be included. Thus, R plus denotes the set of positive real numbers, and Z non-neg refers to the set of non-negative numbers, 0, 1, 2, 3, 4, and so forth. Some authors refer to the set of non-negative integers as a set of natural numbers and denote it as n. That's not true. It's positive integers, not non-negative. 0 is not included in natural numbers. At least that's what I remember learning. I don't know where this textbook got that information, but let's see here. The set of real numbers is usually pictured as a set of all points on a line. The number 0 corresponds to the middle, and it's called the origin. Unit of distance is marked off. Each point to the right of the origin corresponds to a real number, a positive number, and to the right is the negative number. I'm sorry. To the right is positive numbers. To the left is negative numbers. Sorry about that. But it's divided into 3 parts. The set: positive real numbers, negative real numbers, and the number 0. Note that 0 is neither positive nor negative. Give some examples on the number line there. And you thought you escaped number lines in elementary school. They still use them. Set builder notation. Let S denote a set, and let P of X be a property that elements of S may or may not satisfy. We may define a new set to be the set of all elements X in S such that P of X is true. So we denote this set as follows. The set of all, the curly braces, X is the element of S, and such that the vertical pipe P of X is true. So the vertical pipe means it can be read as such that. That'll come up later as well. So given that R denotes the set of all real numbers, Z is the set of all integers, and Z plus is the set of all positive integers, describe each of the following sets. So what would this set be? And is it finite? That's a question for me. For me, yeah. Yes. Now, is it finite or infinite set? Is it infinite or finite? No, it's infinite because there are infinite number of numbers between 2 points if they're real numbers. With integers, that would be different. So what would the set for the second one be? That one is finite, yes. What are the elements?
X is equal to all integers such that it's greater than -2, less than 5.
Okay, so what elements are those? -1, 0, 1, 2, 3, and 4. Yeah. And the last one, just the positive integers? What would the elements be? Uh, 1, 2, 3, 4. Yeah. Yeah. All right, let's see. It goes through it, and this is you use the number line to pictorially represent the values on the number line, indicating that they are members of the set. Using the open end instead of the dot on -2 and -5 to show that they are not inclusive. And the second one, -1 to 4, and then just 1 to 4 for the third one. Subsets. Okay, a basic relation between sets is that of a subset. If A and B are sets, A is called a subset of B, written like this with this stylized C with the line under it. This line here, that's important. If and only if every element of A is also an element of B. Symbolically, this here means that for every element X, if X is an element of A, then X is an element of B. The phrases A is contained in B, or B contains A, are alternative ways of saying that A is a subset of B. It follows from the definition of a subset that if that for a set A not to be a subset of B means that there is at least one element of A that is not an element of B. So with the line through it, the not subset means that there is at least one element X such that X is an element of A and X is not an element of B. Now, the line under the stylized C here indicates a subset. There's also a proper subset where A is a proper subset of B if and only if every element of A is in B, but there's at least one element of B that is not in A. So they can't be equal. This is basically, this symbol here says subset or equal, kind of like the less than or equal sign symbol that you see in math. This is a subset or equal. The proper subset would be A, the stylized C, B, without the line under it. That would be a proper subset. They don't, for some reason in the slides, they don't use that, they don't show that symbol. Don't know why. Let's see. Let A be the set of positive integers. Let B equal be the, and these slides mess up on some equations here. Let B equal to the set of integers greater than or equal to 0 and less than or equal to 100. And let C be the set of 100, 200, 300, 400, 500. Let's see here. Is B a subset of A? Are the integers between from 0 to 100 a subset of positive integers? No, because 0 is not. This includes 0. 0 is not included in the positive integer set. Yeah, little details. That's math loves details. Is C a proper subset of A? Did I hear a true out there? Yep, it is, because all of these elements are in the positive integer set, and the positive integer set contains other values that are not in C. See here. Is C a subset of B? No, because there's a lot of elements of C that are not in B. Is C a subset of C? Remember the line underneath means subset or equal. So it is true. That is true. It's here. False, because 0 is not a positive integer. True and true. Let's see here. And false and true. Which of the following statements are true? 2 is an element of 1, 2, 3. Is an element, not a subset. Is an element. Yeah. So that is. Is the set of 2 an element of the set of 1, 2, 3? No, because that's a set. This set does not contain a set. This is an element. So that's. But is 2 a subset of 1, 2, 3? No, it's not, because the subset operator here is between 2 sets. This is not a set. That's an element. So that's false. Is 2 a subset? The set of 2 a subset of 1, 2, 3? Yes, because it is comparing 2 sets, and 2 is in this set, so it does have that. Is 2 a subset of this? No. It is a element of that set. So this one would be correct. So, yeah. Oh. So it'll go only A, B, A, D, and F are true. And they go through each one individually. We already did that. Cartesian products. One of the more annoying things about sets, because it can lead to a lot of writing and that sort of thing. But anyway, given the elements A and B, the symbol A comma B in parentheses denotes an ordered pair consisting of A and B together, with the specification that A is the first element of the pair and B is the second element. 2 ordered pairs, A, B, and C, D, are equal if and only if A is equal to C and B is equal to D. So It means, yeah, this here symbolically. So is 1, 2 equal to 2, 1? No, it's ordered. Now this is more like an array. An array with the element 0 being 1 and the element 1 being 2 is going to be different from the array with element 0 being 2 and element 1 being 1. Let's see here. Is 3 comma 5 over 10 equal to square root of 9 over 1/2? Yes, because the elements evaluate to the same value. So why this silly question's in there is, what's the first element of 1, 1? 1. There's both 1. So why? Anyway, kind of a silly question in there. So, so yeah, no for the first one, yes for the second one, for equality. And yeah, the first and second elements are both 1. Hello. So now the notation for an ordered n-tuple generalizes the notation for an ordered pair to a set with any finite number of elements. It also takes both order and multiplicity into account. So an ordered tuple would be like an array in C++. It's only it's with denoted with the parentheses instead of the curly braces. So the order does matter, multiplicity does matter, and you would call it like a ordered 10-tuple, for example, for 10 elements, or an ordered pair for 2 and an ordered triple for 3. They're only equal if each corresponding element is equal in value. So element 5 in one has to match up with element 5 in another for them to be equal, so on and so forth. Let's see here. So are these equal?
No.
No. That's an easy one. This one? Are those equal? Yes, they do evaluate to be the same. So, yeah. Yes, they are equal. Now, Cartesian product, this is where it gets mildly annoying. You have multiple sets. The Cartesian product, denoted by the stylized X here between the sets, is a set of all ordered n-tuples where A1 is an element of big A1, A2 is the element of the set A2, etc., etc. So you have this symbolically representing the set, but it's a set of ordered n-tuples. Usually you don't deal with more than ordered pairs, typically by hand. Computers can easily do Cartesian products of larger sets, but they get very large very quick. Let's see here. So, for example, x, y, and 1, 2, 3. The Cartesian product would be the set of all ordered pairs that you can make with these two sets of elements. x1, x2, x3, y1, y2, y3. You take the number of elements in each set, 2 and 3, multiply them together, that's how many ordered pairs you're going to get. Every combination possible with those elements. So the So here would be curly brace, x1, x2, x3, y1, y2, and y3, close curly brace. See why I say it gets kind of mildly annoying. A lot of writing and for putting this is a lot easier than writing all this stuff out. But yeah, there's going to be 6 elements because 2 times 3 is 6. So 1, 2, 3, 4, 5, 6, and you get down here to a cross product with, not cross product, Cartesian product with B, Cartesian product with C. It's going to be 2 times 3 times 2. So it's going to be 12 elements. So as I recall on my on the test for this, the quiz for this chapter, I don't have you do too much of that. Like I said, it's just you can understand the concept without dealing with the tedious writing everything out. So, but yeah, they do the x1, y1, x2, y2, so on and so forth. They talk about this as they talk about the counting up the number of elements. Oops. So yeah, you can nest them. This is nested, so you'll have an ordered pair in here in the ordered pair, kind of like a multi-dimensional array. Ordered pairs and that sort of thing. Let's see here, and you get the 12 elements of all those. Let's see here. Now, I didn't talk about this. The set of real numbers, Cartesian product with set of real numbers, is going to be the set of all ordered pairs x and y, where both x and y are real numbers. If horizontal and vertical axes are drawn on a plane and a unit length is marked off, then each ordered pair in R, Cartesian product with R, corresponds to a unique point on the plane, with its first and second elements of the pair indicating respectively the horizontal and vertical positions of the point. So what does that describe? The Cartesian graph plane, Cartesian plane that you remember from, I guess that would be Algebra 1 or pre-algebra, covered the Cartesian plane initially, graphing formulas and stuff like that. Yeah, the Cartesian plane. It comes from, I believe it was Rene Descartes that came up with this system of doing things. But another notation, which is important to both mathematics and computer science, denotes objects called strings. Let n be a positive integer. Given a finite set A, string of length n over A is an ordered n tuple of elements of A, big A at least, written without parentheses or commas. The elements of A are called characters of the string. The null string over A is defined to be the string with no characters. It is often denoted lambda here and is said to have a length of 0. If the alphabet of this system is A, 1 and 0, then the string over A is called a bit string, which you'll get into in comp.org and computer architecture, that sort of thing. They do strings, use an example of strings with using the letters A and B. Strings of length 3 over the alphabet A and B, with at least 2 characters that are the same, are going to be AAB, ABA, so on and so forth. It is in computer programming, it is important to distinguish among different kinds of data structures and to respect the notations that are used for them. Similarly, in mathematics, it is important to distinguish among, say, this here, that, because they are all significantly different objects. Curly braces denote a set, parentheses, an ordered n-tuple. No parentheses, no commas, a string. So different data types or data structures have different notations in math. And that will be it for this section. I think I will call it a day at this point. But the next section is relations and functions, and all the fun stuff you can do with those. In the meantime, let's see here. Next Tuesday, there should be a quiz in class on Chapter 1. It's just going to be four sections. The 2 today and the 2 on Thursday, and then we'll cover do the quiz and then start on Chapter 2. The homework. Have you been able to log in and see about doing the homework? I know we haven't covered any topics yet before today, but have you been able to get in and look at the homework? You can do it? Okay. All right. The instructions, I believe, are in the in a link in an announcement that I sent out. Okay. Yeah. So yeah. Homework is due before the quiz on Tuesday. Be ready for that, and we'll, like I said, cover the other 2 sections of the chapter on Thursday. I guess that'll be it. Have a good day. See you on Thursday.